Welcome back to the next video about the details of the amazing MMC5983MA 3-axis magnetic sensor, that thing here. In the previous video we did a deep dive into the innards of the chip, especially its anisotropic magnetic resistive sensors in a wheat bridge configuration. And we also implemented a little bit more code in our library. Card here, link in the description. Now it's time to, start implementing the rest of the functionality that thing offers. Enjoy! Out of the 6 commands that thing offers, we already implemented in the first 2 videos the take magnetic measurement and take temperature measurement. Cards here, link in the description. In the previous video, already carded, link in the description, we implemented the set and reset sensor magnetization commands. So that leaves us with the OTP read and the software reset. Software reset is simply a software reset that includes an OTP read, and the software reset takes up, according to the datasheet, 10 milliseconds. OTP read means that the one-time programmable memory of that thing will be reloaded into its registers. It's really a NOP, so no operation, because the OTP memory contains only zeros, so all registers, when you carry out that in operation, will just be resetted to all zeros. Anyway, let's write the code. So in the header file we have 2 new methods here, bool software reset and bool reload OTP data. They work exactly internally like the other commands, take magnetic field measurement and take temperature measurement, so I'll be quick about it. Of course, we have 2 new bits here for the command bits in the related registers, and the implementation of these methods here in the CPP file do exactly the analog like we already did, for example, for take magnetic field measurements. So we take in the case of software reset, the contents of our control register 1 we have shadowed inside our library, and we OR that with the software reset bit, and then we write the whole thing, that 1 byte, to the control 1 register of our chip. Exactly the same for the reload OTP data, just another register and another bit. However, now that we have a working software reset, we can really write a useful begin method for that library. And this method will just bring our chip into a defined state using the software reset and check if it's operational. Just by checking, we saw that, I don't know in which video, but a link in the description, if the OTP data load was successful by first, of course, reading the status register. And here's the implementation of our begin method in the CPP file. So we do first, we saw that software reset. If that fails, we return false. Then we wait the prescribed 10 milliseconds until the software reset is done. Then we read the status register from the chip. If that fails, we return false. And then we check if the OTP data load was successful. That is, the bit was set in the status register. If that is not the case, we set our last error variable to, that's a new one here, new member in our enum. In our error enum, OTP data load failed, and then return false. Otherwise, if everything was fine, we return true. And here's that additional member in our enum here, OTP data load failed, with a numeric value 6. That's it. Our setup function now looks a little bit more professional because we have now here a line MEMSIC5983MA dot begin. And if that fails, then we just print out with the function we saw that in previous videos, zero print error in software reset. In the loop, to check things out, we have a delay of 100 milliseconds. Then we send a reload OTP data command to the chip, and then we read its status. Of course, zero print error if something fails here. And then we print out if the OTP data load was indeed successful. And that is the output on the serial monitor. Okay, so that X, that was the last serial print for the serial plotter that was left in the setup method function. And then we have here always OTP data load successful equals 1. True, everything's fine. Let's move on to the bandwidth selection, and here we have a 2-bit option in the internal control register 1 between 00 100 Hz and 11 800 Hz. And the bandwidth selection also influences how long a measurement of the magnetic field takes, so between 8 milliseconds and 0.5 milliseconds. The reason being the chip internally averages over several measurements. Anyway, let's write the code for that. In my header file of the library, I define here a num-type bandwidth with the 4 2-bit combinations here between 100 and 800 Hz. Remember, all 0 after a reset, 100 Hz is the default. Then we need a public method here, writeConfig, that basically writes all the configuration data in all the 4 control registers to the chip. I have a setBandwidth method here where I obviously pass as an argument the bandwidth, and that just sets the bandwidth bits in our internal shadow registers. So afterwards we have to use writeConfig to get that over to our chip. And finally, here in the register bits, I define a bit mask constant for our 2 bandwidth selection bits here, the last 2 bits in the control register 1. The implementation of writeConfig is trivial. I just use our writeRegisters method here to write, starting with control register 0, 4 registers over to the chip. I also added the writeConfig here to our begin method, just as a matter of course, to be sure that we really know in which state the chip is. Remember, our array of shadow registers was initialized to 0 in the constructor. Where is it? Here. So all zeros. So the chip should, after a reset, set everything to all zeros in its registers. But doesn't hurt to write again all zeros to those registers. And here we have the set bandwidth implementation, which is also trivial. It gets as an argument our bandwidth, and then I take my control register, that is the contents of my control register, and I binary AND that with not the control, the bandwidth bits in that control register. So I basically reset them to 0, and then I binary all that with the bandwidth argument here, which is of course also a bit pattern, as we have seen. And then I assign that to my control 1 register as new value. In the sketch itself, we also saw that in the previous video, I think. I'm using now a static byte count, which will initialize at the first call of the loop function to 0. And I increment that every time we go into the loop. And then I have here a switch statement on count -1. You remember I had very odd numbers here the last time I used that, so the -1 allows me to use even numbers. So in case 0, I set the bandwidth to 100 Hertz, and then I write the configuration, error handling here. After 50 loops, so about 5 seconds, I go to 200 Hertz, then 10 seconds 400 Hertz, 15 seconds 800 Hertz, and after 20 seconds I basically reset the whole thing and we start anew. The rest is almost as usual as we've used it before. So I take a magnetic field measurement. I wait 100 milliseconds. 10 times through the loop, 1 second. Then I read the access outputs from the chip, and just for now, I just print out the x-axis value, the signed value of the x-axis. And that's how the whole thing looks on the serial plotter. So we start here for about 50 measurements with a bandwidth of only 100 Hertz. Then we switch to 200 Hertz, and you can see there's a little bit more noise. A little bit. Then we switch to 400 Hertz, maybe even more noise, but it's very continuously. And then we switch into that 800 Hertz mode. And two things happen. We have a lot more noise on our signal, and our signal value makes a jump. So be careful when using that 800 Hertz mode, which gives you a measurement, if you want, every 0.5 seconds. It's kind of special, especially if you consider that if we go down here from 100, 200, 400 Hertz, we go down from 8 milliseconds, 4 milliseconds, 2 milliseconds, and then we go to 800 Hertz bandwidth, we only need 0.5 milliseconds. So there's something going on that's not really documented in the data sheet. But let's try to have a closer look at the noise levels, shall we? I'm now printing out in my switch statement in which bandwidth mode we actually are. And I'm printing out now the raw access output as 32-bit, 18 significant bits, unsigned integer in a binary format. And we will have a look at that on the serial monitor. And that's how the whole thing looks on the serial monitor. Lots of ones and zeros, and in between a label at which bandwidth we are operating. I think I have enough data now for a little detailed analysis, so I just pull the plug here from my Arduino, and then we'll have a look-see. If we have a look here at the 100 Hertz data, then we see that we only have noise on the last 4 bits. So that's good. I think I saw, here one time the 5th bit is also flipping, but let's say 4 bits. If we look at the 200 Hertz measurements, it's easy to see that really the last 5 bits are now flipping around. Well, at least the 5th bit is not flipping around just once like in the 100 Hertz data, but more times. So let's say 5 bits. At 400 Hertz, it's still just the 5 bits here, but yeah, the 5th bit is flipping around more frequently. So let's call 200 Hertz 4.5 bits of noise, and 200 Hertz 4.5 bits of noise, and 400 Hertz full 5 bits of noise. At 800 Hertz, the picture changes. I mean, I can see, no, that bit is not flipping. This bit here is flipping, and this is the 1, 2, 3, 4, 5, 6, 7th bit. So we have at least, oh, it's flipping not that often. Let's say 6.5 bits of noise. That's quite a jump, isn't it? To summarize, at the bandwidth settings of 100, 200, 400, 800 Hertz, we measured a bit noise of 4 bits, 4.5 bits, 5 bits, and 6.5 bits, not least significant bits. That were just the last bits in our binary number that were changing around randomly. And measurement time again was 8, 4, 2, and 0.5 milliseconds. So that 800 Hertz mode, yeah, there's something special about that one. Now we can convert the number of bits at the end of our binary number, so our, I called it bits noise, into actually least significant bits noise. So if only our last binary digit flips around, we have obviously 1 LSB bit noise. If the last 2 flip around, we have 1 plus 2, because yeah, the second bit has twice the value, 2 to the power of 1. So we have 1 plus 2, so 3 LSBs noise. And then if the last 3 flip around, yeah, the third bit has the value 2 to the power of 2, so 4. We have 1 plus 2 plus 4 equals 7 LSBs noise. So the general formula for that is that our LSB noise is 2 to the power of the number of bits at the end we have noise minus 1. And if we apply that formula here to our bits noise, we get that LSB noise numbers. So for 4.0 we get a 15 LSBs noise, 2 to the power of 4 minus 1, so 15. And then 4.5 is 22, 2 to the power of 4.5 is a mathematical thing. 2 to the power of 5 minus 1, 31. And then the big jump here, a really big jump, I mean this is a factor of 3 here. 2 to the power of 6.5 minus 1, that's 90. And I round it here, where I have these, not natural number exponents. Now we know that 1 LSB in our 18-bit number is equivalent to 0.0625 milligauss. And that gives us the noise peak to peak, not RMS. That's peak to peak. Yeah, that's the maximum variation, peak to peak. Noise in milligauss, if we just multiply that with our LSB noise. So here 100 Hertz, a little less than 1 milligauss noise, then 1.38 milligauss, 1.94 milligauss, and then the big jump here, 5.63 milligauss. Now, the strength of the Earth's magnetic field, it varies. It depends where you are, but it's in between 250 milligauss to 650 milligauss. So let's take the average 450 milligauss and calculate the percentage of our peak-to-peak noise to the average Earth magnetic field. And this gives us these percentages here. So in 100 Hertz mode, our noise is actually 0.21, only 0.21% of the Earth magnetic field. And at 200 Hertz, 0.31, it's still not bad. Also at 400 Hertz, 0.43. still not bad. I mean, twice as bad as at 100 Hertz. But yeah, that 800 Hertz mode, then we have here a noise level peak to peak of 1.25 of the Earth magnetic field. That's a little bit much for precision measurements. Two remarks at that point. If you look at the bit noise numbers here, which start the lowest, 4 bits at the end of our 18-bit being peak-to-peak noise, I have to revisit the issue about, or the question about, going with the 18-bit numbers we can get out of the chip, probably cutting off 2 bits here at the end, which are just noise, and going for the 16-bit numbers might, in the end, be the better option. We'll see. Second remark. In the datasheet, they promised us a 0.4 milligauss total RMS noise, and we, not measured really, but guesstimated a peak-to-peak noise in the 100 Hertz bandwidth mode of 0.94 milligauss. So yeah, this is not exaggerated. This is a quite accurate number here given in the datasheet. Now, the least 2 significant bits in an 18-bit value really being drowned in the noise, it really got to me. So I wrote 2 new methods here. Raw axis output 16-bit signed and raw axis output 16-bit in Gauss. And I added the 18-bit explicitly to our old function we have already implemented and used. The implementation of the raw axis output 16-bit signed is exactly analog to the implementation of the raw axis output 18-bit signed. I think we did that function in the second video. The only difference being I'm now working here in all the calculations with a 16-bit instead of 18-bit. Exactly the same holds true for the raw axis output 16-bit Gauss, which is analog to the raw axis output 18-bit Gauss, only now I'm working here with the scaling with the 16-bit values instead of the 18-bit values. In the loop inside the sketch, I commented out all the switcheroo stuff with the bandwidth mode. Yeah, we are by default in 100 Hertz mode. And the only other change is that I now output here for the serial plotter our values in Gauss scaled by 1000, so in milligauss and with 7 digits, okay. And that's the output on the serial plotter. So blue is our 16-bit value, or our Gauss value as float derived from the 16-bit value, and red is the value derived in Gauss from the 18-bit unsigned integer. And as you can see, they're almost identical, almost. I mean, there is maybe plus minus 1 bit, but difference, that's to be expected. But if you look at the big picture, so inside Earth magnet field scale, so I'm rotating here the thing. Yeah. Both curves are almost indistinguishable, at least visually. So there is not really a visible difference between the 16-bit and the 18-bit curve. And I expect the noise level for the 16-bit values to be the same. I mean, we just cut off the last 2 least significant bits, but noise is a fickle mistress. And so I reactivated the whole switcheroo thing here between the 4 bandwidth modes. And I'm now outputting here on the serial port the raw access output 16-bit in binary format, and we do some bit counting again. So we have now the same bit dance here as before. Let's have a closer look. At 100 Hertz we now have, let's say 2.5, it's almost 3. I think about it, but yeah, if we are honest, probably 3 bits of noise. At 200 Hertz, the 4th bit starts to flip now and then. We can go a little bit, but yeah, it's almost stable. Okay, there was one flip up here. So let's call 100 Hertz 2.5 bits and that 3 bits. At 400 Hertz, clearly our 4th bit here is now flipping around in the breeze, so 4 bits of noise. And at 800 Hertz, the 5th and 6th bit are also flipping sometimes. But of course, that's a carryover from the 5th bit flipping now and then. Let's scroll down a little bit further. Yeah, there it's stable. Let's call that, happened 2 times, 4.5 bits of noise. Now, if we crunch the numbers for the 16-bit mode and the noise and compare that to our 18-bit mode, there's a little bit of a surprise. So we had for 100, 200, 400, 800 Hertz, 2.5, 3.0, 4.0 and 4.5 bits noise. That translates into LSBs noise of 5, 7, 15 and 22. And we multiply that by now our LSB is worth 0.25 milligauss, 1.25 milligauss noise peak to peak, 1.75, 3.75 and 5.5. And if you compare that, only the first 3 values for 100, 200 and 400 Hertz mode, you see we gained here quite a lot of noise. Okay, so about 50%, yeah, here a little less than 50%, and here we almost doubled it. Yeah, that was in 100 Hertz mode, not really visible, that difference between 0.94 milligauss and 1.25 milligauss noise, but noise is a fickle mistress. And we have definitely more noise in 18-bit mode. The big exception being the 800 Hertz mode. Yeah, that was so awfully bad when we took the 18-bit values, but if we run in 800 Hertz mode and 16-bit modus, we basically do not increase the noise. That leads me to one conclusion. The 100, 200 and 400 Hertz modes should be used in 18-bit mode for maximum performance in regards to noise. While the 800 Hertz mode, that monstrosity here in 18-bit mode, is actually quite good in 16-bit mode. Okay? So, we've learned something about that chip. That's good. They could have written that into the datasheet in the first place. But anyway. To wrap that chapter up, you cannot cut off simply bits and expect the noise level to stay the same. As long as these bits, even if they look like noise, still contain some information, statistically speaking, you will increase the noise level, as we've done here for the 100 to 400 Hertz modes. If these least significant bits you are cutting off are really just completely random, then you are able to stay at the same noise level, but only then. I think I mentioned it one or twice before, but noise is a fickle mistress. And please remember, we are here just visually by counting bits that flipping around in the breeze, guesstimating the noise level. We could have put the whole data into an Excel spreadsheet and made a real RMS noise calculation, but that's not really visual and actually quite boring. So yeah, I didn't do it in this video. Let's move on to the next configuration option here, and that's continuous measurement mode. We have here 3 bits in the internal control 2 register where you can set the measurement frequency between 000 off and 111, 1 kilohertz. Please note 1 kilohertz is only possible if our bandwidth is set to 800 hertz. And 200 hertz is only possible if our bandwidth is greater or equal to 200 hertz. Then we have an additional bit here, enable continuous measurement mode, also in the internal control register 2. And you need to set this bit so that the continuous measurement mode frequency actually does something. So, for example, does a magnetic field measurement every second at 1 hertz. The thing is, these 4 bits are kind of coupled. I can't see any application where you would enable continuous measurement mode, but set continuous measurement mode frequency to 0, or vice versa, choose a continuous measurement frequency here between 1 and 1 kilohertz, but disable continuous measurement mode frequency. And my code will reflect that. In the header file, like for the bandwidth, I have here an enum continuous measurement that defines all the bit patterns here that we can write in these 4 bits in the register. So first, disabled, which is also the default, is just 4 zeros. Okay, so it's disabled, that disable flag is set to 0, and the common frequency is 3 zeros set to off. Then, just for experimentation reasons, later on I have here a constant CM off, which sets the enabled bit but leaves the frequency bits 0. And the rest is just with a enable bit enabled, set to 1, and the bit patterns here for the different frequencies. Of course, like for set bandwidth, I define here a public method set continuous measurement, which gets a continuous measurement enum as an argument. And since I need it in the implementation, like I did for the bandwidth selection bits here, I define a constant expression for the control register 2 continuous mode bits. Finally, here is the implementation of the set continuous measurement method, which is completely analog to the set bandwidth method. So I take the contents of my control register 2 and I binary AND that with the binary complement of my control 2 continuous mode bits, so masking them out. And then I binary all that with my continuous measurement argument here, which contains the bit pattern that I really want in the register. And then I write the whole thing back to my control 2 register. In the sketch, I'm now setting the continuous measurement mode to 200 Hertz here right after my begin, and then I write the configuration, and I also will print out later on the X, Y and Z axis values. In the loop, all my bandwidth mode switcheroo stuff is gone for now. What's also gone is the take magnetic field measurement command. Okay, because we're in continuous mode, we don't need to tell the chip to take a measurement. It should take 20 measurements per second all by its own now. Then I have still my delay 100, and then I read the axis output from the chip as always, and then I print out all 3 axes in milligauss. So I take my 18-bit Gauss value and multiply it with 1000. Let's have a look at the serial monitor. And as you can see, everything is just working as expected. So I'm printing out every 100 milliseconds, that stuff here, and I'm taking a measurement every 50 milliseconds. Wonderful. That's it for today. Next time we just continue with the other configuration options of our little, there it is, chip here. Till then, bye.